Okay, so here we're going a little bit further with Lewis structures. The presentation that you guys are about to see, I want you to be really clear about a couple things, and that's actually going to be on the next slide. So I'll tell you kind of all the nitty-gritty here about what the importance of this particular presentation actually is. So kind of hold that thought while I just explain that what you see here, where it says formal charge and Lewis structures, this is, as it says in black, how to determine the best Lewis structure that you could possibly write. What you're going to see in this presentation is an alternative way of determining a Lewis structure. Everything, listen to me when I say this, everything that I've taught you about Lewis structures will always work and always be correct. This is an alternative. It would be accepted on an AP test, but it is not a requirement. So when you talk about overall importance of this presentation, this is something that it's good to know about. It's good to know what formal charge is. But when it comes to drawing Lewis structures, if you want to continue to do the way that I've already taught you, definitely do it. So having said that, a lot of what I have on this slide is some things that I have just alluded to. So just read it with me, okay? Drawing Lewis structures using the octet rule will always be the right answer. However, the octet rule is not the only way to create a feasible Lewis structure. Formal charge is a second option for drawing Lewis structures that uses the octet rule, but also overrules it to create a more stable Lewis structure. You will never specifically be asked to draw a Lewis structure using formal charge or to explain why a structure drawn using formal charge makes sense. You need to know what formal charge is and what formal charge is based on, but that's about it. So hopefully we're clear on that. Okay, so what the heck is formal charge? It is, as the definition states here, a hypothetical charge. The phrase hypothetical charge, if you think about like real charge, we're talking like an ionic charge. Hypothetical charge means that the atom itself does not have a charge, but in theory, it sort of kind of does. So we'll talk about that more. So it's a hypothetical charge you obtain by assuming that bonding electrons are equally shared between bonded atoms, and that electrons of a lone pair belong completely to the atom to which they are attached. If you need a second to let that sink in, pause the video, reread that definition, and make sure it makes sense. Okay, now moving on. The point of formal charge is to minimize the charges of individual atoms as much as possible, which sometimes means, as I say here, that you're overruling the octet rule, which means you may actually cause something to exceed the octet, which you wouldn't normally do. You may produce additional bonds in places that you wouldn't normally put them. In essence, you make a Lewis structure that looks a little strange, but in fact, it would be actually workable and possible. So when you think about what that all means, again, the octet rule is the 8 electron thing. So what we're going to be doing, starting with the next slide, is determining what formal charge actually allows us, or how we do actually formal charge, how we draw Lewis structures using formal charge. So the first thing we're going to do is, as it says in the underlined portion at the last bullet point, we must write out all possible Lewis structures for the molecule, basically any option that we could possibly think of. So as we go on to the next slide to look at an example, COCl2. So I think it's probably pretty clear by this point that you would put carbon in the middle as the central atom. And so now if you take a moment and write out all possible Lewis structures, and what do I mean by that? Well, let me show you. Here's what I mean by that. If we write all possible Lewis structures, take a look at these. Do you see how these show multiple options? So the first one shows a double bond with the chlorine on the left. And the middle one shows the double bond with the oxygen. And then the one on the far side will show the double bond with the oxygen on the right side. And those are all perfectly feasible options. Notice in all cases that the octet rule is actually upheld for all atoms and everybody's happy. So I guess in all technical realms, each of these would work. But before we continue, which one do you think is correct? Take a second, look at those. Based on rules I've already given you, what do you think is correct? Okay, I have no idea what you said because I can't hear you. But I'm going to assume you did choose one. And we'll see if you're right. So let's see if you were right. Let's find out. Okay, so here's some rules that I want to give you. So for each atom in the molecule, what you're going to do, and I'm going to, by the way, give you the rules here really quick, and then we're going to implement those rules on the next slide with the same COCl2 element molecule that we were just working with. So here's the rules for each atom in a molecule. First thing you're going to do, count the number of bonds around the atom. This is the number of equally shared electrons. You are then going to count the number of lone electrons around the atom because, as the definition said, these electrons belong only to that atom. You're going to then use these two values that you've just calculated by doing the following. You'll take the number of valence electrons, you will subtract the number of bonds, and then you will subtract the number of lone pair electrons. And that value that you get out of step 3 is the formal charge, and you are supposed to write it in a small little circle that you put right by the atom. So if you want to maybe record these quickly or just jot these steps down, it might be helpful to have them in front of you as we go on to the next example. So here's how these rules actually work when we go into the example. Okay, so here's what we just did, right? We have our 3 different structures with a double bond placed in all 3 positions. And again, you already made your choice of which one you think is probably correct based on what we've already talked about. And then up here at the top in the yellow, formal charge, I can't remember why it says Fe. Formal electron charge, something like that. Number of valence electrons, minus the bonds, minus the number of lone pair electrons. So here's how it works. If you take a look at the chlorine on the left, okay, so Cl left, this one right here, would you agree that chlorine has 7 valence electrons? Oh, goodness, I hope so. Would you agree that there are 2 bonds? Oh, I lost my cursor. There are 2 bonds, okay, so there's where the minus 2 comes from. And then the number of lone electrons, well, it's got 4 dots around it, so that would be minus 4. So 7 minus 2 minus 4 is a formal charge of positive 1. So we'll put a little positive 1 in a circle beside the chlorine. Okay, so do you kind of get the hang of it here? So we're going to continue on, and we'll go to the chlorine on the right side. So notice in this case, same 7 valence electrons, but there's only 1 bond, and it actually has 6 lone electrons. And so in this case, the formal charge is actually 0. Ooh. Okay, next, how about the oxygen? So 6 valence electrons, 1 bond, and 6 lone electrons, and that is going to give us a formal charge of -1. And then finally the carbon has 4 valence electrons, 4 bonds, and then no lone electrons, which equals all out to be 0 and a formal charge of 0. So what you are looking at now is me sort of double checking to see, is this a really good Lewis structure? So you might notice here at the bottom the note, the sum of all the formal charges must equal the charge on the molecule. Okay, well, that works because the charge on this overall molecule is actually 0, right? And 1 and -1, those equal 0, those cancel out. So the whole charge is actually 0, which works. And that's the first thing to sort of just double check that you did your math right. So next, let's check the next structure. So start with the chlorine on the left. So 7 valence electrons, 1 bond, and 6 lone electrons, formal charge of 0. Okay, try the chlorine on the right for me if you would. You don't even have to do that much work because it's actually exactly the same as the one we just did. So formal charge of 0. Now the oxygen is different, so could you take a second, pause the video please, and calculate the formal charge of oxygen. Okay, hopefully you calculated the formal charge to be also 0, 6 minus 2 minus 4. The carbon really is no change because that is still 4 bonds with 4 valence electrons, so formal charge of 0. So what's the difference between these 2 structures? What do you notice? I'm listening. Oh, yes, I think you did notice it. So you have a +1 and a -1 here, but over here you've got all zeros. Oh, that's interesting. That's very interesting. Well, can you predict what's going to happen over on this one? because by the way, this one is exactly the same as this one. So really, you're just flip-flopping which chlorine is going to have that positive 1. So let me get all this up there. So again, if you need to, take a second, pause the video, verify that you understand where these numbers actually came from. Because then the next chart or the next question I'm going to ask is, okay, so what does this all mean? And that's where we're going to have a little more discussion. So pause the video if you need to just double check or do anything, and we'll move on to the next slide about what does it all mean. Okay, so how do I choose the right one? Because now I've done this work, I've written 3 different structures, I don't know which one is right, and I've taken time to calculate all these formal charges, so now what? Well, I'm supposed to choose the structure with the lowest magnitude of formal charge. So for instance, if you look at my example, I say let's say I have a -2 formal charge on atom A, and I have a -1 on atom B, and a -1 on atom C. Well, those all equal out to be 0, right? And that's what it needed to be. But the flip side of that is, what if I had a structure that had all zeros anyway? So that would be lowest magnitude of formal charge. All zeros are better, and that structure would be the one that I would choose. So right there, that kind of tells you which structure is the correct one. When 2 proposed structures have the same magnitudes of formal charge, choose the structure in which the most electronegative atom has the negative formal charge. And that should make sense. You are sort of doing a little matchy-matchy kind of thing, and making sure that the electronegative one has the negative charge. So, given these sort of rules for, how do we handle the work we've now done, if we go back to this, I hope you would now agree that it's the one in the middle that's the choice. And hopefully you chose that one from the beginning, because what we're doing is we're actually treating twins the same. Here's a chlorine and here's a chlorine, and they're being treated exactly the same with 6 lone electrons and 1 bonded pair, and then the oxygen is the one that's asked to double bond. If you look back at your notes, you will also see that there was a discussion about which atoms double bond, and chlorine is not one. In fact, oxygen is a double bonder, and here it's double bonding. So hopefully that example makes sense, because what I'm going to ask you to do next is a sample. So if you would do me a favor, go ahead and try sample 8.10. It's on page 389 in your textbook. Try it first. Don't look at the answer. Don't look at the answer in the book, that is, and then I will show you the answer after you try it. So pause now. Okay, so here's the answer that you should have come up with. Maybe something like this, right? Because if you do your regular old octet rule, this fulfills everybody's octet. Everybody's really happy, right? But let's try something. Let's do formal charges. So if you calculate the formal charge of xenon, 8 minus 3 minus 2, and again, the 8 is the valence electrons, 3 is the bonds, 2 is the lone electrons, you get a formal charge of positive 3. If you look at all the oxygens, they're equivalent with negative 1s, and so when you put it onto the structure, you can see that that's a pretty steep magnitude of formal charge. They all end up being 0, but that's pretty high magnitude. So my question for you is, can we do better? And what your ideas might be. So hopefully you could maybe think of, all right, so I need to, I've got to reduce the formal charge, increase the formal charge of the oxygens, and I've got to decrease the formal charge of the xenon. Let's see. What if I make all the oxygens share with xenon? What if I give xenon more bonds? Which, by the way, as it says here at the bottom, xenon can exceed an octet. Remember that xenon is one of those ones, along with krypton, that tends to exceed an octet. If I created a structure that looked like this, which, by the way, is totally strange, right? It doesn't make sense. It's not something that you would ever think of drawing. But actually, if you base it off of formal charge, this would really be the best Lewis structure. Now, I want to stress again, this structure at the top, the one that you probably drew to start off with, it's correct. It's totally correct. You would never lose credit for that. But based on formal charge, this is an option. So it's kind of a strange little thing. Don't forget the little lecture I gave you right at the beginning of this presentation, that it's really all coming down to understanding what formal charge is, but the octet rule thing always works. So Final slide of the day is a little homework helper. Wait, flip the page and see what the book did. Think first. It's less work. Oh yes, do this. I don't have a textbook in front of me right now, but I am remembering that the textbook definitely does something kind of funky. So take a look and see what the textbook did. But what I did on this slide was what I would call think first. And we actually did less work because of it. So that's cool. So last slide is, as it says at the top, a homework helper. What I would just say to you, as you are going to come back to class tomorrow, this is a slide that we may want to work with to help us with homework a little bit. You only have 3 problems for homework, I do believe. So just a couple of little things that might help you with homework. So we can handle that tomorrow. And I guess that's it. So we'll see you later. Bye-bye.